Are you studying material science, or are you just making mechanical engineer or chemical engineer and do not know what and where to specialize? Or do you know some studying these subjects and not really aware of where to go? Then listen up. This episode is dedicated for you. In this episode, I have invited two brand new engineers. They have been studying material science, and they've just finished their master project. And this episode is about the master project. If you're interested in learning what is possible to do as a part of your study, this is it. It is pretty amazing. These guys, they have moved some barriers that I'm sure you did not think of, but this is possible if you are studying material science. So jump on board, because we also need you in the industry afterwards. See you soon. Hi guys, welcome to the podcast, Everyday Metallurgy.
Thank you. Thank you for having us.
Yes,
yeah, it's a
Simon
pleasure
and
being
Matthias, you are new guys on this show. In fact, you are so new because I was centering your final exam. You have been studying for a master's degree in material science, and this summer you presented your work, and I loved it. So therefore, you got an A. It was a very nice presentation, but the best of all, I invited you to tell about your work on this podcast, because I think everybody else should see what young guys could work on. Because one of the backgrounds for having this podcast is that I would like to show the young people like you how fascinating it is to work with material science. Stop all that language or psychology. You should work with materials, because that is the future. Can it be more clear
it's so
where the
fascinating.
future is? But would you start giving a short presentation of yourself and your background?
Yeah, I'll start by quickly sharing here my screen here. So as we can see here, my name is Simon, and I've studied together with Matthias here, and we both did a mechanical engineering degree here at DTU, and then we switched to materials and manufacturing engineering for our master's thesis.
Yeah, so I think me and Simon, we met each other the first time on the first day because we were put in a group together, and the rest is history. So we've worked on a ton of projects together, and are really good friends and collaborators in terms of working on several projects, both with industrial partners and also just academic projects. And yeah, I remember that we both did mechanical engineering, and then we I think it was me that pulled you and convinced you to do materials and manufacturing after we both agreed upon that mechanical engineering was great and fun, but it was more academically rigorous in terms of only working on either structural dynamics or fluid mechanics, whereas materials and manufacturing gave us a broad and interesting overview and a lot of the whole process structure from an idea to getting a product, and a lot of quantities of this product out into the real world, which is what we find most exciting.
Yeah, and also the manufacturing aspect. We both love additive manufacturing or 3D printing. So I first started 3D printing when I went to 7th grade, and working with 3D print throughout my education, the different levels, it also meant that I was really interested in this manufacturing part, and we have great facilities here at DTU for that.
I recall getting my first 3D printer during study in 2019, and ever since then the capabilities of both the deposition printers with thermoplastic that you can have in your home to the crazy big printers that we're working on today, it's been quite the journey. And as Simon says, we have a great facility, in parts due to the great faculty we have here at DTU that have really established from just a small room where it was just the weirdos who came to this huge laboratory that's state of the art with a ton of different types of printers that are all worked on both by industry and student projects together because of this large pull and this interest that there is in the world of additive. Yeah. So,
but should we jump into the theme of today?
Yes.
You have worked on laser powder bed fusion on an alloy called 174PH. It's a stainless steel that typically is precipitation hardened. But you have tricked around with it and made it, I leave a cliffhanger. You have tricked with it. You have made some funny things with it that I haven't seen before. But should we start looking into the laser process? How does it work?
Yeah, we can start if I go here to. We had a few projects here, but if we go through to here with the powder bed fusion, I don't know, Matthias, if you want to start talking about how the process works.
Yeah, so I think by now most people are familiar with laser powder bed fusion. Just as a quick recap, however, essentially what's happening is you have a metal powder on a bed where you have a laser up top, which is melting this powder, fusing it together in a sequential layer by layer process where you have a recoater that comes and scrapes a new layer across. So you're building up 2D prints, so to speak, of fused metal up into a 3D object, slice by slice. And so there's a ton of complex phenomena going on in this process, most of which in our project we've been able to circumvent due to our great PhDs and other colleagues that have done a lot of work in this area. But essentially in the processing window, you need to ensure that you're getting a good fusion of the powder. So if you go back one slide, Simon, you can see that you either have lack of fusion, which is when you have no or incomplete melting of the powder. Then you have your process window, which is the green area here. And on the red area, you're getting keyholing where you're over melting your melt pool. Yeah. So if we go back up to the next slide, we can see that illustrated here on the left-hand plot here, where essentially what you have is generally researchers look at scanning speed and laser power as the two parameters that they try to change in order to find the proper processing window given what they're using. A very simple way of looking at it would be via the energy density equations, where you have P for power, V for scan speed, and L for the layer height. Whereas there's a lot other parameters, such as hatch spacing being the distance between the two lines that you have as rasters that are going between each other, and that can be various different methods of doing so, as you can see on the 6 examples that we're showing below.
Yeah, and when we talk standard, if I go purchase laser powder bed fusion machine, I am not free to play with all these parameters. Some of them are locked from the supplier, but you have been able to play with a machine that is open. Can you tell a little about that machine? Where does that idea come from, and how does it look?
Yeah, so if I just quickly go here to, we have the OpenAM project at DTU, where at DTU they designed a printer that from the bottom up is made by commercially available parts and an open firmware, so you can actually do, in theory, everything you would want to do. So if you think of the commercial 3D printers, the powder bed fusion printers, they're made for being simple. So in the industry, what you want, most companies want, is just a plug-and-play solution. And whenever you simplify a process, you also limit the amount of things you can do. There's a reason why, if you look at computers, Apple with their MacBooks are very popular for home computers, but big data centers, they use Linux because they have the freedom. And it's kind of the same here. Once you have the simplified version, you can't do the research that is critical for universities.
Just want to do a quick interruption to show you guys the AM lab here at DTU. So if you follow me inside here, we have a range of different AM platforms here, and also some general workspaces. And up here you can see the sketches of the OpenAM platform, which was developed here at DTU. So over here we have a binder jet lab, we also have an SLS printer, and if you follow me in here, we have our powder bed fusion platform. And here you can see some of the prints that have been made on this powder bed fusion platform here at DTU. And all these prints are made on the OpenAM Loop 1. And in here, you can see both the OpenAM Loop 2 printer we have right here, which is a powder bed fusion printer. This is developed here at DTU. You can see we have a powder bed platform, rollers at the back. And this is the second iteration of the OpenAM platform, where the one we utilize for our testing is over here, which is the first iteration. And here we have a setup with a cheap galvo and laser. And if you look inside, it's actually a print ongoing right now. So as we mentioned in the podcast itself, this is an open platform, meaning that everything can be changed just as you want it, which is really great for research. So quickly to show you guys how this printer works, in here behind the hatch, we have a build plate here that moves up and down, and we have a roller here at the back with a hopper where powder is distributed and rolled out here over the build platform. Then we have a nitrogen gas flow across here, and we have a laser up here at the top, which does the local melting of the powder. Over here we have the control platform, where right now the software isn't open, but it's a line-based, code-based platform we have right now. So it's not the most user-friendly, but because it's an open platform, you can do anything you want.
So, while this layer finishes printing, we can go see the final 3D printer that we're making, Loop 3. This will be actually CE marked and ready for a drop-in at a Danish vocational school. So we saw Loop 1 being printed now. So let's go over and see our final printer being built currently. It's fully available on GitHub. You can just scan this QR code right here if you want to download the project files. This printer will be CE marked, meaning that it's safe for untrained users to use and operate, and then it will be sent out to a Danish vocational school when it's finished being built. This allows full adaptability by the users and replacement of parts if something were to break. Same optical system, the same build chamber, the same mechanical components are on the machine. The only thing that's been upgraded is the screen and also the safety features, as I mentioned. Once this is finished being built, the last printer DT will build, but then it will be shipped. Then it's ready to be downloaded on GitHub and being used by any user that wants to adapt the system for their own needs. Exactly, and an even better example would be 2D printers. I mean, just common page printers, right? If you go and buy the toner ink and whatnot, you're locking yourself into a system, and you have to buy these refill packets. The printer might be cheap, but the refill packets are expensive. You have to use the manufacturer's service and technicians and whatnot, and you're very limited in what you're able to actually customize. And the same goes for 3D printers. So this research project has a big funding from a Danish public interest fund, which has funded this because industry wants to look into what is possible when you go beyond the confines, as well as supporting future research. So this is meant as a base for other research institutions to work on, where they have essentially full control and a very cheap platform. The BOM of this printer is only is slated to be $40,000 US, and so that means that you have a lot more possibility, both in terms of budget, but also in terms of what you can do on this printer. And if something goes wrong, the replacement parts can be found on common marketplace areas rather than specialized industrial partners where you can wait a long time to get replacements. But this, however, means that you have to be self-sufficient, essentially, right? You can't just call somebody that will fix it for you.
Yeah. So what have you done on this machine that differs from what you can do on a traditional machine?
Well, in order to actually answer that question, I think we need to give a quick introduction to what our project actually was, the one that we had for a master thesis. And
yes.
The background of that project is, as you see here, there's a Micro-AM logo here. This logo was made with the steel that you mentioned earlier, where normally it's a martensitic. Yeah, normally it's a martensitic stainless steel. But when you 3D print it, you have some other properties of it, because you have such a small cell structure that the martensite formation is actually suppressed. And in addition, you also have, in our stainless steel here, it was nitrogen atomized. So when making this powder, you normally have a big melt pool where you blast it with a gas to create these small powder particles. And when using nitrogen, you actually get a higher nitrogen content in the powder, which stabilizes the austenitic phase. This meant that we actually had a print that was austenitic even though it was a martensitic powder. And then we used the thermal strain to induce strain-induced martensite in the print. And therefore, by varying the thermal gradients during the cooling, we could actually get localized martensite formation and localized austenite, retained austenite. And traditionally, when doing these kind of prints, what you would do is, as you create these parts here where you want to have two different phases, we call those functional graded materials. When doing these two different zones, you would actually have in a traditional printer slicer, you would have to have two different objects in order to have two sets of process parameters. But what we could do is we had an open platform, so we could create our own slicing, where instead of just having one set of process parameters per object, we could vary it per layer or even for one scan line. So in the middle of doing a single laser scan line, we could actually just ramp up the power or ramp down the scan speed to get local higher energy.
So essentially, to build upon that, you can see here on the right-hand side picture that this OpenAM logo, which is being seen through magnetic viewing film and a magnet, to be able to print that text where you have a martensitic phase that's ferromagnetic and the rest behind that is a bulk paramagnetic, it looks similar to the metal top view picture we have on the left. But in order to print that, you do it sequentially. And so what happens when you do that is around the red on the text, after you're printing first the start of it, which is the metal cube around it, and then you're printing the text in it. And so what you're getting is you're going to get built up porosities and other defects that are occurring as you have edge effects. So that is also what happened in the previous papers on this area of being able to tailor specific phases, where they experienced a large amount of cracking at the interface between the martensitic and the austenitic areas, because of porosities that were building up and leading to cracking. And so we set out to address this in a novel method.
Yeah, can you disclose that? Because now I want to go nerdy. What parameters do you use to control these different structures?
Well, if we start with the parameters, we can go back to what we talked about before, where we have normally you use the power or the scan speed to adjust how much energy you're putting into an object. We went one step further and also looked at the duty cycle, which is how, when you have a pulse laser, the duty cycle is the percentage of on time. And by doing that, you can also modulate the laser power by turning it on and off. And we use these three parameters as they are dynamic parameters that are not geometry based. So when you change the hatch spacing or the layer height, if you do that dynamically, it will have geometrical effects, and therefore we chose to look at those three specific parameters.
And how fast can you change these parameters? Because the laser is running pretty fast.
So if we go over to our volumetric slicing, essentially, or we can go here. So essentially what happens is that we're looking at how we change the parameters in situ. So if you look here at A, we see that this is a conventional slicing where you're doing it sequentially. So you have your first object being the green, and then you're printing the red hatches, and then they're disconnected. However, what we devised is we do it in situ. So we ramp up either the power or ramp down the velocity, or we increase or decrease the duty cycle. And in doing so, we have different machine response times. So if we look at what we have slated as the machine parameter response times for the given system that we're printing with, the OpenAM system, we can see that duty cycle ramps up in an order of 10 microseconds, below 10 microseconds, from going from a low energy density to a high energy density, which is what we want when we want to promote martensite. Whereas if we're doing power, it's a little bit slower and might even overshoot a little bit as the power stabilizes due to control mechanisms. Whereas scan speed takes a long time, almost 0.4 milliseconds, which is a long time, and that's just due to the inertia of the mirrors that are positioning the laser, having a mass, right? And so they take time to stabilize and move. And so in doing so, we theorized that duty cycle would be the fastest parameter in order to get these sharp transitions between austenite and martensite. Yeah, but maybe we should also explain how we devised the volumetric slicer.
Yeah, just quickly, I want to add that these numbers, these times, response times, they might seem very low when we're talking not just milliseconds, but sub-milliseconds and microseconds. It might not seem significant, but when you're looking at a very fast scan speed, so we only printed at 400 and 600 millimeters per second, but in the industry, they go up to several thousands millimeters per second. You actually see that these times can be significant distance when you move at that fast speed.
Yeah.
But But what we then did is we tried to find a way of, instead of having this, as Matthias mentioned, the edge effects where you print one object where you have edge defects and then try and start a new scan line, you will always have defects. They tried to overlap them to get some remelting, but you still saw some porosities. So what we did is we didn't slice it as two different objects. We sliced it as one, and then we defined a region where we modified the parameters. So as I've shown here on screen, what we did is we defined a boundary geometry. And whenever a scan line would cross that boundary, it would then get this ramping of either the power or scan speed or duty cycle. And it led to an effect as shown in the second picture, where there's a single scan line going through everything instead of being split up to avoid edge effects.
But you are still within the process window that you started, the green arrow. You're not going into layer of fusion or into pinhole creation.
Yeah,
exactly.
Yeah, so that's the difficult part of this, because we are using the energy, the thermal gradient, to try and create the difference of martensite and austenite. So we use a higher energy to get the martensitic transformation. And when we do that, we obviously have the process window we have to stay within. And that's been one of the limiting factors for how low can you go in martensitic content and how high can you go in martensitic content. You have to try and find that process window you can stay within. And that's where you have to look at other processes like post-process treatment to get the higher martensite content.
Yeah. So if we dig a little deeper into what is happening when you do that, when you add more heat, what will then happen? Because my understanding is that the formation of martensite is controlled by the cooling speed and the martensitic start temperature when you reach that. So how does this influence the cooling rate? Because if the cooling rate is the core of the creation, this is indirectly affecting the cooling rate. Can you elaborate on that?
Yeah, so quickly, you mentioned the martensite start temperature. And that's the thing about this process, is because we have a very small cell structure when doing 3D printing, the martensite start temperature, we actually suppress it so much that it's not really a concern here. We don't actually get any thermal martensite. We only get strain-induced martensite. But the strain-induced martensite is coming from thermal strain. So that's how we're actually using the thermals to create strain-induced martensite and not the thermal martensite. So that's why you can use the higher start temperature you have, the more extreme the cooling will be, and therefore we get a higher strain. And this is the way the cooling works is you have a massive build plate that you build upon, and you have a very large thermal mass, and that means you have incredibly rapid cooling rates in this powder bed fusion,
like a heat sink.
Yeah,
exactly. And furthermore, you have the powder, which you want having to be highly spherical, because you need flowability of the powder as you're drawing it across the build plate with the recoater. And so the spheres have very low contact area, so they're actually not conducting a lot of heat out between them, between where it's been printed and where it's unprinted, or the laser has touched the material. And so essentially you're looking at in very high cooling rates that are on an order of magnitude higher than what you get in conventional manufacturing processes. And so this is what we're abusing, so to speak, to generate thermally induced strain martensite rather than the
Yeah, and then you also mentioned previously the nitrogen. How does that affect the microstructure? And a tricky question: will the nitrogen stay in the metal when you melt it, or will you change the amount of nitrogen during the process?
That's actually a very interesting question, and we had a PhD student who was doing some research on the same machine at the same time as us, and he used the same powder that wasn't nitrogen atomized but argon atomized. That means that during this powder fabrication, you didn't have the nitrogen content increase in the powder. and he would still not get the martensite, but he would get ferrite instead of austenite. So that's the interesting thing, is it's actually, when you don't have the martensitic phase, the nitrogen helps to give us austenite instead of ferrite. And we can see that the nitrogen content actually is, from other research, fairly similar in the after print and before the print in the powder.
Mm-hmm. But so the EOS GP1 powder, if you can go to that content.
Yes.
So the EOS stainless steel GP1 powder, which is what we've been printing with, and what other researchers have also printed with, who've been able to induce this magnetically graded material. It's actually funny because 17.4 does not per se slate what the nitrogen content has to be, and so when we're printing in the inert nitrogen atmosphere around the laser build volume. And also this specific powder, which is actually old powder, not the newer GP1. So EOS, I think, realized that their GP1 powder, which was nitrogen atomized, was creating was promoting austenite, and so getting an austenite prints when you have a martensitic stainless steel is a little bit off-putting. So they moved over to argon atomizing the powder. So we have our little old vintage stock of old powder that we're hoarding, almost like a wine collector, because we can use this to create unique geometry, or to create this unique phenomenon, which you can't do when you're using just argon promoted powder, or at least it becomes a little bit more difficult. And that's just simply due to the nitrogen promoting the austenite phase more than the martensitic phase.
Yeah. Vintage powder, that's a new.
Yeah.
It's quite funny how you can use like what used to be a defect is what we actually saw as an opportunity, and other research saw as an opportunity to create these functional gradings. And it's quite funny how that works sometimes.
Exactly. And just to go and just to say one thing more, is that Freeman, which is the author of the paper that we were very highly inspired by in terms of being able to generate this magnetically graded material, experienced these porosities that were causing a motor stator to crack. And so this is what we set out to kind of solve, was how could we do what she had done, but while decreasing the amount of print defects. So we actually had a usable part that didn't have to be stabilized with epoxy, but could come off the build plate and be used by in electromechanical or electromagnetic applications, such as a motor stator, which is a good example. Yeah.
So now we have talked theory. Does it work? Did you succeed in doing what you just explained?
Yeah, we actually got some pretty good prints I can try and find here. So we created some samples where we tried to have a martensitic core and an austenitic outer shell, and then we did a sample where we did it the old way we mentioned of having two geometries, and then our new slicing method, and compared them. And what we actually found was, if you see here, these were some cross-sectional pictures we took of light optical microscopy. And we had taken an etchant here, which was a coloring etchant. And this coloring etchant called Beraha, it colors martensite, but not austenite. So you could get a visual contrast and a quick way of seeing, do we actually get a phase difference? And there we could also use the grayscale intensity to try and measure if we actually had a difference between the phases. So it's the difference in how dark the areas were.
And so what we tried looking at was using the three parameters, both scan speed, 2D cycle, and power, in order to see what the interfacial sharpness would be between the two phases. So we used a sigma 3 threshold for the grayscale intensity, and we defined that as being the interfacial width. And in most applications, you want that in functionally graded parts to be as small as possible, as tight as possible. And so that's what we also looked at.
Yeah, so if you look here at the here we have the interface we detected is you can see that the old sample, it was really dependent on the porosities, the detected interface, because we used the grayscale, and porosities they are black or very dark in the images. But when looking at just the microscopy pictures here, images here, the micrographs, you can see that the porosities in the interface looks lower for sample B, C, and D than sample A. There's a significant amount of porosities in sample A. Yeah. And what's interesting is you can actually see in sample A that the martensitic part was what was printed first, and then the other part, the austenitic, afterwards. And the porosities are in the martensitic part here. And you can actually see all these porosities are from the initial edge effects. And when then trying to create the second print afterwards, you didn't get the porosities, but you have a lot here in the interface, which are the critical areas. Yeah.
Exactly. And with this being the A part being the conventionally sliced parts. Yeah. Another thing that was also very interesting in our work was yes, we managed to get it to work, and we managed to get this volumetric slicing where we go across the part and then we ramp the power up to get to promote each phase region. But what we also discovered was the difficulty in metallurgy prep of this part, because you have a metastable austenite. So just being able to cut and grind it as you do in metallurgical sample prep is not quite as easy as you would think.
No, I could imagine when if you heat it up, the austenite will be the remaining austenite will be transferred to martensite.
Actually, the thermal heating afterwards, if you don't go too high in temperature, you could actually stabilize the austenite a bit by because what happens here is once we print it, we use the strain to create the martensite. But so we always have some strain in the parts, and the more strain, the more martensite. And when you actually anneal it afterwards, you saw that the austenite would get more stable as you remove the stress, and you have a larger threshold for when you moved into the martensitic zone. But what was the main difficulty here is the results here we showed. If you look at the image D here, which was the duty cycle, we actually didn't see a visual difference across the zones. And we thought that was probably because it didn't work, the duty cycle ramping. But then afterwards, we actually used a different method, which is called a ferrite scope, which is a magnetic induction method where it measures the magnetism of a larger bulk of the material, so a 5 millimeter conical area. And by having this larger area, we actually saw that the martensitic BCC fraction here, it was actually similar in the duty cycle as it was in the other samples, meaning that we just couldn't see the visual difference, but it was still measurable. That's something that was a bit mind-boggling at first. And how can we see it on one and then not measure it?
Yeah,
and that's actually,
So this is actually, we used the ferrite scope after initial XRD because we had sample prepped our and cut our samples across and done XRD scan lines across the interface to see what we were looking at. But we thought, wow, we've generated a difference between martensite and austenite content of 20% plus, and this was great. You'll see it with actually quite a little bit lower. We still got a difference, but it wasn't quite as drastic. And we still need to put in a little bit more work, a little bit more printing time to be able to get a bigger delta between them. There's also some other strategies that we can come into later. But essentially what happened was due to the sample prep, we're actually generating a lot more of a, we were generating in the austenite, we're tripping that so-called trip effect into martensite. So what we were looking at was artificially lifted up in terms of the difference rather than what we actually were getting if we looked at the not just the surface sample, but actually going into the material. And so so this is also another key finding of our research, is that not just using surface analysis, which a lot of the other papers in this field have done, but looking at either vibrating spectral microscopy, BSM methods, or high energy XRD, or you looking at hysteresis, or this ferrite scope approach that we used, which is actually just a tool that you use actually for checking welds in industry on the fly, was really good at getting us a bulk measurement rather than just a surface measurement, which is what misled us initially.
Yeah, because we even did electropolishing and fine hand polishing, followed by electropolishing, everything we could do to try and minimize the effect. And no matter what, we still saw with the finest electropolishing, XRD actually, we had some initial results before we started. Using the same process parameters as our highest energy density zone, they got 40%. But here we saw 2% with the ferrite scope. That's quite a large of a difference. And what we think is when you have these, here is a picture from the Freeman paper, where I've tried to overlay the lines of where our energy densities roughly would be. And what happens is when you try and move these both by a bit of mechanical deformation, if you move both of these lines, the one that's 2% goes into an exponentially increasing area of martensitic content, meaning it might look like 20, but the one that's 1% then becomes an area where it looks like 2%. That's why we could see a visual difference between the zones, even though there's 1% difference in actual content, even though on the micrographs it looked like a 50-60% difference.
Exactly.
Now this is called Everyday Metallurgy, so I would like to relate it to applications and where can you use it. And we also during your exam talked about other materials to go for, because this is so sensitive, so it might not really be applicable in the real world.
Yeah, exactly.
So we should turn this to where should we go to make this usable in the real world?
Exactly. So emptying out the wine cellar, so to speak, of the vintage old stock of material. Eventually it will run out, so we need to look at new avenues to find other material that we can use this to exploit the same principle. And
yeah, so one of the initial things that was here that you also just mentioned is the actual application. We need to make this usable, as we have such a small operation window and we have low stability of the austenite, as we just mentioned here. And one thing that ongoing research at D2 is looking at is other methods of doing in situ heat treatment. So that's where once you've printed a layer, you take the laser and you do a secondary pass where you also do a very low wattage, very low power, and you can do heat treatment locally. And there you can actually do a very low temperature heat treatment to anneal the austenite, remove the stress, get it more stable. But you can also help get a higher martensite fraction by doing a heat treatment and also doing the tempering of the martensite in situ and still create it in a 3D structure instead of having to rely on a furnace afterwards where you can't do localized heat treatment. So we actually, the ongoing research is getting closer and closer to getting a very, very high fraction difference while also having actually a decent stability of the austenite.
And if we look at materials in general, you have been working on the 17.4 pH, but could other alloy systems be of interest for making these graded functional materials?
Yeah, definitely. You could also look at other stainless steels where you don't necessarily have the martensite-austenite difference, but just having localized precipitation hardening or something like that could be something you could look at. Else you also have titanium, which is something that a lot of people are looking at for additive manufacturing right now, where you can have your alpha and beta phases, you can have your martensitic titanium, and you can also use the process parameters or different kinds of in situ parameters like localized nitriding to try and stabilize each phases. And there's so many different methods. We just went to a conference called NoLamp, which is the Nordic Laser Conference here at D2 this year, where we were presenting our results here as part of a paper we did. And we heard so many different researchers talking about in situ, this and that, and different methods of shock peening or monitoring or synchrotron, where you do X-ray while printing, and all these kind of things they could do. Is also a way you could somehow get other materials to create these functional gratings, because it's not just different phases, it's different functions, mechanical properties.
Yeah.
And so essentially it all comes down to the high cooling rate that we have in our material, and that we can exploit, whether if we print at a high energy density and are getting a material that has a slower cooling, or whether or not we get sorry, I lost that train of thought. I will get
so that's the way we did it with the thermal grading, but you can also do it in so many other options, as I mentioned, like shock peening or localized nitriding is something I know other universities are looking at.
Yeah, I was also thinking of playing with shape memory alloys.
Yeah,
because the nitinol material, it's a very precise mix of nickel titanium, and if you are just a little off in the, I think it's 49, and then some additive percentage. But if you're just a little off, 49, 51, then it changed the temperature where things happens. So you can locally, when you 3D print the shape memory alloy, you can locally evaporate more of one substance than the other, and then change the chemical composition. And just by varying it little, you can move to another temperature where the shape memory alloy is affected.
Yeah, it's funny you mention it, because we actually had conversation with 3 different people during this conference that actually looked at shape memory alloys in 3D printing and laser powder bed fusion.
Yeah.
So there are other actually researching this, but also with magnetic memory alloys. And there's many different ways of optimizing the process parameters, looking at the crystal structure, which you can also vary by having the different temperatures or post heat treatment. And localized changing. When does this shape memory function actually happen?
So in this work you have done, what will be next step?
Well, we just finished this as our master's thesis. So there's not much more we can do. I think we're always welcome out to DTU and play around with the printer and have fun with that. But obviously going into labs, especially the labs that we've used throughout this project, costs money. So what's next for us though is that we hope that being able to implement this and have this documented with this novel volumetric slicing, so to speak, or not to speak, this volumetric slicing method, is that we spoke with a lot of researchers at NOLAMP, this Nordic Laser and Materials Processing Conference, showing them what it was that we could do, rather than having these sequential defects areas that you get when you're printing, that we can hopefully, especially with this OpenAM or other printer manufacturers, that where there are maybe some hacks to go into the material or the code of the printer and be able to print continuous in situ changes during each individualized vector line of the laser, and being able to modify the energy density and create these functional graded sharp effects. We hope that we can, at least, especially coming onto this podcast, inspire some people to look into this method, because we see a great potential in being able to make magnetic components, but not just magnetic components. We can also make other types of functional grading, whether that's sharp or whether that's a slow grading. We can essentially be able to modify what type of microstructure at what area we want, so we can go very long and have a very slow grading, or we can have a very sharp grading. It all depends on the power and the inputs that we're putting into the material and at what point throughout a print vector.
Yeah, as Matthias mentioned there, that's why we try to create a sharp interface, because once you have a sharp interface, you can always just make smaller steps of localized increases to get a smoother interface. But for this project right now, even though we are not working on it anymore now, we know that DTU are continuously working, and when we know they are aiming at getting close to 100% martensite while having fairly stable austenite, and they believe it's feasible. We believe it's feasible by doing these post-treatment in situ, like the heat treatment. And once we have that, our hope is that the industry will start looking at the applications of this, because we need an application in order for industry to start using it. And as long as industry is not using it, we won't see these commercial printers implement this, because you can't do this on a commercial printer with our slicing method. And our slicing method is working, and we hope that will increase the amount of research and hopefully work towards getting these functional graded materials getting to market.
And at the very least, increase the amount of downloads that we get on the OpenAM project, and hopefully maybe inspire at least one person to purchase the BOM wherever they want, and build the printer, and maybe make some changes, and create this community of people making their own metal 3D printers. And I know at DTU with these subsequent heat treating processes that come afterwards at each layer, that we only got almost a 2% BCC volume fraction percentage, but being able to heat treat, I know another researcher has gone up to 80%, which is quite high, right? And so being able to go even further at 100%, potentially, but even if so, there are boundless of different methods that can be different applications that can be used, because in conventional manufacturing processes and heat treatments, you can generally only create on the surface, on the outermost surface, you can create different phases, right? Whereas in here, we can create phases that are intersecting through the component or are in the inside of the component. And we can generally, just with a laser, wherever we can touch with the laser, wherever we're printing the part, we can essentially choose what type of phase composition we want at that given point. And I think that is what's the most interesting, is that we have full autonomous control. And hopefully, if everything goes right, you can circumvent the heat treating process entirely. You can remove your part from the build plate and then plop it into whatever component or application you need without doing any post treatments afterwards.
Yeah. And you can have a fully stress-free component when you take it out of the printer, instead of having such a component that is fully stressed.
Exactly.
I've seen a lot of prints where when you take it out, it does like that.
Yeah, that's the thing about the laser powder bed fusion here, is we have a steel print plate that we print directly on to have good adhesion, so the part will stay where it is. But this also means that the stress will be in the material during the print. You don't have the stress relief, so you might not see warping, but when you then cut it, you have the internal stress, which is can be really, really difficult to handle.
So the last question is more personal. Are you satisfied with the education you have taken, and is there a future for the two of you using your education?
Yeah, definitely. I couldn't have chosen a better career path or education path so far. So I've always known since I was young that I really love doing these small projects. We're doing these engineering kind of projects in my spare time. I mean, just looking at around my room, I have a 3D printer stuff everywhere, and I've always loved doing these projects. So definitely the right education for me. And we've had so many different companies working with Lego, for example, and GN, massive companies. We have this exposure, and there's actually jobs now at the end as well. Even though additive manufacturing isn't the biggest industry yet, we have so much knowledge in other manufacturing methods and mechanical methods that it's actually fairly easy for us to find jobs, and we can just enjoy our hobby as a job now. That's the cool part.
Exactly. Just to expand on that, if we go back to the slide about us, if we look at what it is we've gotten the exposure to do, just the two of us in our 6 years time at DTU, I think we've always had the knack, right? And this knack has been just super fertilized at DTU. Obviously, the first year, which is the hardest year of engineering school, in my opinion, I had a lot of imposter syndrome, wondering if I was cut out for this, because it was very hard and very, very theory forward. But as soon as I developed a study discipline, it only got more fun from there. I mean, the amount of great projects that we've been able to work on with exciting companies. DTU has very good relationships with these companies that look forward to working with students and getting their input, and if not anything, also free R&D time to use our great equipment and facilities to help improve their products and their processes. So it's been great through and through. I couldn't have asked for a better place to be, and the amount of, ability to control whatever we study ourselves. We're able to do self-developed courses where we come out to a professor, pitch an idea, and the professor is on board or not, and will help us guide our ideas and our course objectives throughout the learning process. So it's been a great place where we've been able to be autonomous and also have a ability to set out and essentially do whatever we think is most right in our education and our professional life. And I think that's a really good lesson, taking a step back and thinking about it for just maybe, we spoke last 1.5 months ago, but being able to reflect on this and realize that this autonomy has really given us this self-sufficiency in us being curious and wanting to go out and explore, and working with both exciting companies but also projects, and being able to do very interesting things throughout the course with great facilities and great professors that are all very passionate in what we do. That's been super rewarding, and I think I'll look back at my 6 years with a smile, because it's been nothing more than excellent.
Yeah.
And
you said some of the nice words that is also fueling the Everyday Metallurgy podcast and myself. Curiosity and passion. You can start on very low level, but curiosity, passion, and the right amount of time, you are up there.
Exactly. That's also a point that I was about to say, that I remember one of my old teachers, he always said, as long as you're just curious about things and you have this urge to know, you might not need to have this high level of understanding of the theory, because again, you can actually get there with not the highest level of theory. You can still create interesting projects. And even if you're not necessarily one who's getting the top grades in school, it doesn't mean that you can't get an engineering degree. It's all about just having that passion and curiosity. So definitely sometimes just take a leap of faith and go into it, because we definitely think it's been so fun to study at DTU and have this hands-on experience, not just the pure theory all the time.
Exactly. And one word of advice maybe to any student that or person considering doing a degree, is that I don't know why you would be on Everyday Metallurgy without a engineering degree of some sort, but being able to go out and try and being autonomous and having the ability to do whatever you want in life and pursuing this to a high standard, which is self-imposed. There's no professor that will come and whip you and say you need to go out and do better. You need to. It's all up here. It's all ourselves that are pushing ourselves to try and do interesting and exciting things. And so doing that is very difficult, but it's very rewarding at the end, knowing that it's the fruits of your own labor and not the fruits of external factors that have caused you to get where you are. I think that's what I would say is the best takeaway of taking this degree.
Thank you. I really enjoyed the conversation, and I also hope that you will be strong ambassadors of the Everyday Metallurgy community in the future.
Of course, we find it so interesting, everything with metals and materials in general, because it's our passion. It's not just an education, a degree, and a job. It's our passion working with these kind of things, and we are a bit nerdy. So of course we'll make sure that we stay tuned for all the rest of the episodes, as other people should do as well.
Yeah, exactly. And as a shameless plug, if anybody has any questions or any comments or wants to know more, please reach out to us either on LinkedIn or find us in the comment section. I think we'd both love to respond. And if not, I hope you enjoyed listening.
Thank you very much, and enjoy the rest of the summer.
Thank you. Bye-bye, Peter.